In today's tutorial, we're going to evaluate this sum using simple techniques. This sum is simply based on the technique I'm going to apply here is simply based on this. First, I'll how to make use of the double sum I have here, which first one starts from A and the second one from B. So let's say the sum contains an inline function of, let's call this function A and B. So the next step, I'll try to reduce it so it will take this function, so I'm using A of a different function this time, of only A. Then so at the last, I'll have what my sum is. So from here, I would like to convert it from the double sum. I'll convert it to a single sum, then to whatever it converges to. So let's get to work. Alright, welcome. It's time to apply the first step. So here now, first thing I'll do is to modify these thing here. In this first step, I'll be using integral calculus. So before I make use of it, let me modify this function here. Now, note that 1 over A plus B to the power of 3 is still the same thing when I write minus 1 square times 2 factorial multiplying minus 1 square times 2 factorial dividing A plus 3B to the power of 3. Okay, now I didn't really change much. If these two can cancel out, and then I'll get the original. Alright, so from here I'll have here, this gives me, meanwhile this is 1 over 2, this one is 1 over 2 because 2 factorial is 2, so this is half of. Now in this case, this is the same as the second derivative d over dA of A, second derivative of A. So now I have second derivative of A plus 3B. So in this case, since the differentiation is done with respect to A, 3B is referred to as a constant. So I continue. Another thing you should notice that 1 over A plus 3B is equivalent to the integral from 0 to 1 of x to the power of A plus 3B minus 1, dx. So I'll just impute it here. Let me erase this part. Oh, sorry. Let me remove this part. So in here now I'll have that this is the same as half of the second derivative with respect to A of now the integral from 0 to 1 of x to the power of A plus 3B minus 1 dx. Okay, now from here we already know that this derivative is done with respect to A. have now, let's focus on that first. The second derivative with respect to a of x to the power of a, because the reason why I'm doing this is because it is only x here that is working with a. Other x to the power of 3b minus 1 has nothing to relate it with this, so it's just like a multiplier. Okay, so now let me continue from here. Note that differentiation, the derivative of x to the power of a is the same as x to the power of a ln x. So the second derivative now will now be differentiating for the second time of x to the power of a ln x. Since ln x here, ln does not have anything referring to a, does not have any a variable in it, so I can bring it out first. I'll have ln x multiplying the derivative of x to the power of a. Now, what did I have here initially? Derivative of x to the power of a is x to the power of a ln x. So here I'll have ln x multiplying x to the power of a ln x. So I'll be left with x to the power of a ln square x. Okay, now let me erase this part, for this is the only thing I need. Okay, let me erase these parts. So what will I have? At first, let me still continue by writing these things down. I have that this is equal to half of the integral this time around. The integral of the integral from 0 to 1 all into, what do I have here? X to the power of a first, x to the power of a plus 3b minus 1. Then what else is remaining? Ln x, ln square x, ln square x. Alright, so I've gotten exactly what I need. Let me erase this other one so it was standing away in the future. So now my aim is to replace this with these expression now. So let me go back to my sum. So my sum now will become, since half is just a constant, and if you look at this sum, what is considered is only a and b, so I'll only write my half here, my half, then my integral from 0 to 1. So what else does it not consider? Ln square x, because there's no a and b here. Then here is x to the power of minus 1, which is same as 1 over x. So what I'll do here is just, first I have ln square x all over x. So this is it. Now what else is remaining? If I look at this, my integral now, this is still remaining, but they have a and b, 3b. So what I'll do is to put them inside the sum. Then I'll first write my two sums now. I have the sum to infinity of a from 1 and the sum to infinity of b from 1 also of what? X to the power of a plus 3b. Remember, this have already been taken out, so I have of x to the power of a plus 3b. Okay, so what next should I do? So the next thing I'll do is to bring in the last element here, which is dx. So this is dx. Okay, now I've done a very important part of this sum, but there are still more need to do. So from here, let me erase these parts, for I've already used them. So I've already used them. Okay, so now look at this sum. There's something I'm going to do now, but without taking the whole expression here. This sum have sum to infinity of a from 1 and then the sum to infinity of b from 1 all into x to the power of a plus 3b. Okay, now let me, since this only has the components we're looking for this sum a, then here only b is needed, so b cannot escape this sum. What we need to do is to share it for the two sum. So now I'll be having a from 1, okay, up to infinity of x to the power of a. Then for the second sum, this is sum to infinity of b from 1 of x to the power of x to the power of 3b. Now something else is going to happen. If you know from the sum of geometric series, the sum to infinity of a number n from 0, which expanding x to the power of n, which expanding this I'll have x to the power 0 plus x raised to power plus x raised to power 1 plus x to the power of 2 plus x to the power of 3. This continues up to infinity. So from sum of a GP, this is the same as 1 over 1 minus x. Now consider our own sum. Now let me work with this first one. Our own sum is starting from 1. So what happens? This will normally start with x to the power of 0. So when it starts with x to the power of 1 plus x to the power of 2 plus x to the power of 3. So, and it will not also be equal to. So what do we do to find what is actually sums to? So what I'll do now is to add x to the power of 0 here. We already know that x to the power of 0 is 1. So then at the end of the sum to infinity, I'll come and subtract my x to the power of 0. So this is the same as writing 1 over 1 minus x minus x to the power of 0, which is 1, minus 1. Okay, so I'll quickly do that for this sum and for this other sum. So what I'll be having is so now let me apply it for this one. So I have that this sum here, continuing with this identity, I have 1 over 1 minus x minus 1. Okay, now multiplying the second, which is 1 over, in this case, x to the power of 3b is the same as x to the power of 3 to the power of b. So I have 1 minus x to the power of 3 minus 1. Okay, this is it. This is one of the things I need. Let me erase these parts if I've already used them. Please, if you're enjoying this, don't forget to give this video a thumbs up. Alright, so from here I'll just continue. Is it not best I use this expression? Don't worry, let me write it out again. I have that this sum is still the same as half of the integral from 0 to 1 of ln square x over x multiplying these two sums, but this time around I have them in the form. I have them in the of this, which is 1 over 1 minus x minus 1 multiplying 1 over 1 minus x to the power of 3 minus 1. Okay, so with respect to x. So let me erase this part. Okay, now 1 over 1 minus x minus 1 is the same as 1 minus 1 minus x all over 1 minus x, and this is the same as 1 minus 1 plus x, x all over 1 minus x, which is same as x over 1 minus x. So in a similar way, one over 1 minus x cubed is equal to x to the power of 3 all over 1 minus x cubed. So I just got the knowledge from this. So let me apply it here. Okay, so now I have that this is the same as half of the integral from 0 to 1 of ln square x all over x. Then here, this one gives me multiplying x all over 1 minus x, then multiplying the next one, which is, let me erase this, x cubed all over 1 minus x cubed. Then what next? What's next? Dx. Then I can take this away. Thank you very much. Alright, something is gonna happen here. Look at this. What do you think they'll do? Cancel out. Let's go. Alright, the next one I have that this is half of the sum from 0, integral from 0 to 1 of x cubed all over 1 minus x multiplying 1 minus x cubed ln square x dx. Okay, so what next I'll do now is to decompose this into partial fraction. Okay, so decomposing x cubed to the power of 3 all over 1 minus x multiplying 1 minus x to the power of 3 into partial fraction, I'll be having 1 over 3 1 minus x squared minus 1 over 3 multiplying 1 plus 2x plus 3x squared all over 1 minus x cubed. Okay, so will this space enter for all of them? Yes. So let me start with this. So while decomposing this integral into partial fraction, I have that this is 2 times 3. 2 times 3 is 6. So I'll have 1 over 6. Okay, of the integral from 0 to 1. So here I'll just put my ln square x, for it is not part of the partial fraction. I have ln square x all over 1 minus x to the power x squared dx. That is for this first one. Now for the second, I'll have minus 1 over 3 multiplying the integral from 0 to 1 of ln square x of 1 plus 2 1 plus 2x plus 3 2x plus 3x squared all over 1 minus x cubed. Right? This is it. Okay, then my dx. Okay, I've successfully splitted this integral here. So what next do I do? First, let me consider this. Note that we already know that 1 over 1 minus x is same as the sum to infinity of n starting from 0 x to the power of n. Okay, now if I'm taking the derivative of the both sides, I'm to differentiate the both side. The differentiation with respect to x of 1 over 1 minus x is equal to 1 over 1 minus x squared. Now if you bring it to this sum side, this summation, I have the sum to infinity of n from 0 of the derivative with respect to x to the power of n. So x derivative of x to the power of n is the same as this is sum to infinity of n from 0 of n multiplying x to the power of n minus 1. Okay, now if you notice, when n is to start from 0, if you multiply n here and then n, it will cancel out because here n is 0, so 0 times anything is 0. So from here I'll have to change it. My sum will now start from 1. I hope you understand what I did. Please, if you find any parts of this tutorial confusing, do what to express yourself in the comment section. Okay, so from here I'll just bring in this into this place. But I'll start by erasing these parts. Okay, alright, so this will now become 1/6 multiplying the sum till infinity of n starting from 1. Sorry, this is 1/6 of the sum to infinity of n starting from 1 of, now instead of writing n x to the power of n minus 1 alone, now x is not alone, it is inside this integral, so I'll bring in my integral now. The integral from 0 to 1 of x to the power of n minus 1 ln square x dx. Okay, so on this other part, this part, I'll just give my sum. We already know that 1/1 minus x is the same as the sum to infinity of n starting from 0 of x to the power of n. So when it is 1/x cubed, it will now be 1/x to the power of 3n. So that is what I'll do now. Okay, so this now is green minus, sorry, this is supposed to be 1/6 minus 1/6 of the sum to infinity of n from 0 of the sum of the integral from 0 to 1 of x to the power of 3n multiplying ln square x 1 plus 2x plus 3x squared. Okay, dx. Alright, so now before I continue, let me work with this sum first. Now there's something called that you should, before I introduce that, let me go back to our memory. Something I did before. Remember that the derivative, remember the other time I used n, but here I'm going to use n. The derivative of x to the power of n is equal to x to the power of n ln x. So the second derivative, just like I did before, will now be ln square x cross now. What's your problem? What's your own? Cross now. Do fresh cross. Oh, Jesus Christ. It's in the room. Imagine. Now, imagine. This integral now will be the same as the integral from 0 to 1 of the second derivative of x to the power of n. Now, that issue permits that I can bring out this derivative outside the integral. So this is now the second derivative multiplying the integral from 0 to 1 of x to the power of n dx. Okay, so this is it. Let me quickly apply it here. Okay, so here I have this is equal to 1 over 6 of the sum to infinity of n from 1 of n again, then the second derivative of the integral from 0 to 1 of x to the power of n minus 1 dx. Okay, so this is it. Now for the second integral, a different thing happens here. Please pay attention. The derivative of x to the power of a n. Now, okay, let me use k n plus b. Take notes, nothing concerns b here, so this is the same as x to the power of b multiplying the derivative of x to the power of k. Now watch what I'm going to do. This is very important. So this is the same as, so now be x to the power of b multiplying x to the power of, sorry, x to the power of k to the power of n ln to the power of n ln x to the power of k. Now there's no big difference between what I did here and what I did in the other sum. It's just that the other time it was only x to the power of n, but this time it is x to the power of k n. Okay, that's why there are changes here. So at the end for this one, I'll have x to the power of k n plus b times ln x, remember, in logarithm, the logarithm log a to the power of b is equivalent to b log a. So that is what I'm going to do here. I can just, this is x to the power of k, right? I'll just leave this k and bring it out and write it, let's say somewhere here. This is same as k multiplying this. So now if I do this differentiation for the second time, it will not be the second derivative of this. This time around, this x, ln x, will be squared. I'll have, let me go back to this place, x to the power of k. So this time around, it will now be ln x to the power of k square. So I'll have k square x to the power of kn plus b times ln square x. The reason for it is k squared. After applying the logarithm rule here, I'll have k ln x, but it is squared, so I'll have k square ln square x. Okay, that is it. So this was not meant to be part of what I need. This is exactly what I needed. So from here we now know that don't know that the second derivative of x with respect to n of x to the power of kn plus b is equal to this. So yeah, I'll resolve to wherever I have, let me divide both sides by k squared. I'll be left with 1 over k squared multiplying the second derivative of x to the power of kn plus b is a better way to represent x to the power of kn plus b ln square x. Okay, so why did I bring all these things? What's the essence for all these things I'm doing now? I'm just looking for something better to use and replace this sum. Now watch, if you look at this, let me extract the integral first. Let me extract this integral. I'll have that this is an integral the same as the integral from 0 to 1 of ln square x multiplying x raised to the power 3n plus 2 x raised to the power 3n plus 1 because of this, plus 3 x raised to the power 3n plus 2. Okay, all into dx. So I'm quickly going to apply this formula that I just derived here. So this is now going to be, if you notice, in this case k is 3 x raised to the power 3n. All this while I've been using x raised power kn. So here k is 3, so I'll just write that this is same as 1 over what is 3 square, 9, all into the integral from 0 to 1 of x to the power of 3n. Now my b can be any number, can be any of these numbers here, sorry. So I have integral of x raised power 3n plus 2 x raised power 3n plus 1 plus 3x raised power 3n plus 2, okay, all into dx. Then on this other part I have minus 1 over 6 multiplying, what do I have here, 1 over 9, all into the sum to infinity of n from 0 of what again, the second derivative of the integral from 0 to 1 of x to the power of 3n plus 2 multiplying x to the power of 3n plus 1 plus 3 multiplying x to the power of 3n plus 2 dx. Okay, so this is it. So the next thing I'll do here is evaluate this integral. That is actually the next step. So here, evaluating the integral, I'll have 1 over 6 multiplying the sum to infinity of n from 1 of n multiplying, okay, let me do this partially. Okay, let me just continue. D squared d squared over dn squared of, now remember that the integral of x to the power of any number n is equal to n plus, x to the power of n plus 1 all over n plus 1. So in this case n is n minus 1, so what am I going to have? This is going to be x to the power of n all over n. So my integral is from 0 to 1, so this is going to be evaluated from 0 to 1. So I have replacing x 0, first is 1 times power n over n minus 0 raised power n over n. So this is 0. I'm left with 1 over n as the result integral. So let me just erase here. will place what I needed here, what I need here. Okay. Okay, so for this other part, okay, I've not taken this out. Now, for these other parts, this integral will be, just know that the integral from 0 to 1 of x to the power of 3n plus any k dx will still take the form of x to the power of 3n plus k plus 1 all over 3n plus k plus 1 evaluated from 0 to 1. So first is to substitute x for 1, which will give me 1 over 3n plus k plus 1. Then substituting x for 0 is 0, so I don't need to do that. Let me just erase this part, make use of the one I need. Okay, 9 times 6 is 54. Oh my god. So I have 1 over 54 multiplying the sum to infinity of n from 0, then the double sum, the second derivative, d squared over dn squared of, so what will I have here? For the first one, I'll have 1 over 3n plus 1. Remember, I'm still applying this rule. In this case, I have no k is 0. So in the other one, I have plus 2 multiplying from 2 over 3n plus 2. Then for the third one, I have plus 3 over 3n plus 3. Alright, so this is it. Remember, we are still under differentiation. But before I continue, I'd like to do something special. First, let me go to this side. Note that the kth derivative of any number, let's say n, any variable, let's say n, of 1 over n plus b is equal to minus 1 to the power of minus 1 to the power of k times k factorial all over n plus b to the power of k plus 1. If you can remember, in the initial stage I made this or something like this, so this is the reason. Okay, back to my question. Alright, we can go, thank you. From here I'll have that this is equal to 1 over 6 multiplying, okay, in this case I have second derivative, so k in this case is 2, so I have here to be minus 1 square times 2 factorial multiplying the sum to infinity. Sorry, this sum looks ugly. The sum to infinity of n starting from 1 of n, which I've already been here for long. Then this is going to be, remember that the second derivative of n plus b, like I said, will be minus 1 square 2 factorial all over n plus b to the power of 2 plus 1. Now, in my case here, b is 0 because nothing is added to n, so I'll just go ahead and write times 1 over n to the power of what is 2 plus 1? 3, so cube. Okay, now on the other part, I'll have this. My writing is not balanced. I'll have 1 over 54. Okay, still the same derivative here. I'll have minus 1 square multiplying 2 factorial all into the sum to infinity of n starting from, okay, I skipped something. Now notice that n here has 3 multiplying it. One thing I would like to do is to first factorize the 3. So I'll have 1 over 54 times 3 all into the sum to infinity of n from 0 all into the second derivative of first n plus 1 over 3 plus 2 over n plus 2 over 3, and then for the third one, 3 over n plus 3 over 2, 3. So for what use is writing 3 over 3, I'm just write 1. Okay, so I can quickly apply the technique we've learned. So this part here is 1, and dividing it with this, I'll be left with 2 here. So I now have 1 over 3 from here all into the sum to infinity of n starting from 1 over n squared. Then this other part I have minus, now 54 times 3 is 162, so I have minus 1 square, because it is still second derivative, times 2 factorial all over 162 is gonna multiply the sum to infinity of n from 0. Now, of 3 different expressions here. The first expression says that it is 1 over n plus 1 over 3 to the power of 2 plus 1, 3. The second expression says that it is 2 all into n plus 2 over 3 to the power of 3. Sorry, this is plus 3 all over n plus 1 to the power of 3. Okay, now note something. I'm introducing functions now. Note this: the sum to infinity of n from 0 of 1 over n plus 1 to the power of any s, or I rewrite to say that it is the sum to infinity of n starting from 1 all over n to the power of s. It's still the same thing, because here if you input as n as 0, the sum will start from 1, then n as 1, the sum will start from 1. This is the same as a function in math known as zeta s. Okay, just notice. So this one looks familiar. This looks familiar. So this is one over 3 zeta. Sorry, okay, zeta function. Zeta 2. Now, just let me bring back the sum for zeta function. Zeta s is equal to the sum to infinity of n from 0 of 1 over n plus 1 to the power of s, or I'll say the sum to infinity of n starting from 1 of 1 over n to the power of s n to the power of s. Okay, that is for zeta. Okay, now a second one that I'm going to introduce here is known as Polygamma function. It is defined as Polygamma m of z is equal to minus 1 to the power of m plus 1 times m factorial all into the sum to the infinity of n from 0 of 1 over n plus z to the power of to the power of m plus 1. So this is what Polygamma function is defined as. So since I've already applied zeta function here, I can go ahead. Now 2 over 162 is the same, okay, as, for a particular reason I won't divide this by this. Okay, come on, we just defined something now, and if you watch this is sum of n plus 1 over 3 cube, and sum of n plus 2 over 3 cube, and sum of n plus 1 cube. So I'm not going to divide by 2, so I'm going to use my 2 here. Now if I change this is same as 2 plus 1 when here is positive. Okay, so that is that. So I have 1, okay, plus 1 over 162. I already have 2 plus 1 and 2 factorial. The next thing I'll just do is to apply my Polygamma function here, here, and here. Now this is the same as please, Polygamma function when m is 2 is known as Trigamma. So this is the same as Trigamma 2. Okay, Trigamma 1/3, then plus 2 Trigamma 2/3. Okay, now plus 3. I'm not going to apply Trigamma function here. I'll just go straight to the point. Remember that I defined zeta function to be this. So this is the exact same I'm having here with respect to the sum. So I'll just have 3 zeta 3. Okay, I've made use of these things, so let me just erase them. We are gradually coming to the end of the first trick to applying this to solve this sum. Alright, so I have from here, this is 1/3 zeta 2, then 3/162 is equivalent to, oh, it's true, something happened here. I only used 2 factorial for these ones, but for zeta 3 it is not supposed to obey that same law with them. So let me still go back to this place. I'll still go back to what I have before, minus 2/162. Okay, times the sum to infinity of n from 0 all over 3 over n plus 1. The reason I'm doing this is because it is only for Polygamma functions reason. That's why I used 2 factorial and 2 plus 1 here. That's the reason why I did it. So from here I have 2 times 3 is 6, so 6/162 is equivalent to 1/27, then my zeta 3, because this sum is the same as the sum for zeta 3, then plus 1/162 multiplying this. Now let me simplify. Note that digamma 1/3 is equivalent to minus 26 zeta 3 minus 4 pi cube all over 3 root 3. Now then trigamma 2/3 is equivalent to 4 pi cube all over 3 root 3 minus 26 etc. 3. Notice how this became the seems to be the negative of this. Okay, never mind. From here I have Trigonometry 1 over 3. What is Trigonometry 1 over 3? It is minus 26 zeta 3 zeta 3. Then what else? Minus 4 pi cube all over 3 root 3. Then from here, what else do I have? Plus 2 trigamma 2 over 3. So I have plus 2 all into what is trigamma 2 over 3? Minus 4 pi cube all over 3 root 3 minus 26 zeta 3. Okay, right. Sorry. Okay. Alright. So this is 1 over 3 zeta 3 minus 1 over 2 1 over 27 zeta 3. Then here I'm having minus 14 over 27, sorry, minus 13. If you evaluate minus 26 minus 2 times, okay, plus 2 times minus 26 all over 162, you get minus 13 over 27. So here I'm having minus 13 over 27. Then zeta 3 and from here I'll have, after evaluating, minus 4 pi cube over 3 3 and then 4 pi cube over 3 3. You have, okay, let me just bring out the coefficients of pi cube. I have minus 4 over 3 root 3. 2 times minus 4 is minus 8, so I have minus 8 over 3 root 3. So this is this is minus 12. Okay, please, I left an error here. This was not supposed to be negative, this is positive. So this case is positive. 8 minus 4 is the same as 4, so I'm left with 4 over 3 root 3. Now if I'm to multiply it by 1 over 162, I'll be left with 1 over 162 multiplying this is the same as this multiplying 1 over 162. So rationalizing the third there, I'll have 2 root 3 all over 7 to 9. Okay, that is by the way. So from here I'll have plus 2 root 3 all over 7 to 9 by cube. So these two adds to give me 1 over 3 zeta 3 minus 14 over 27 zeta 3 plus 2 root 3 over 7 to 9 by cube. Alright, I hope you enjoyed this part, the first part of this tutorial. If you really did, I want you to go over to the comment section and just comment. Go there and express yourself. Do you like this first part, or which one do you prefer, the first or the second? If you actually like this, don't forget to give me a thumbs up. Don't worry, wait for the second. We've been able to prove there are some here, a double sum here, double sum of a plus 3 a 1 over a plus 3b cube is equivalent to 1 over 3 zeta 3 minus 14 zeta 3 plus 2 root 3 over 7 to 9 pi cube, which is what we had in our question here. Okay, thanks for watching this first part. Get ready for the second. Now, before I start the second one, I want you to do something for me. Just guess a number, have a number in your head. I'll just give you two assertions that will definitely work for that two numbers you've guessed. Alright, time for the second. Everyone, the second technique. So don't forget the number I told you to guess. We'll use it maybe at the middle of this tutorial. Then I'll make the two assertions that must always work by assumption. Alright, from here, let me do something crazy. 1 over a plus 3b to the power of 3. What if I factorize the 3 here? I have 1 over 3 multiplying a over 3 plus b cube, which is the same as having 1 over 27 all into a over 3 plus b cube. Okay, let me just bring it in here. This is equal to 1 over 27 multiplying the double sum of first. So the first starts from a equals 1, then the other one b equals 1. Okay, now let me write this here. 1 over a over 3 plus b cube. Okay, now I can still rewrite this sum right here. So let me say, let's b n plus 1. So that here I have, since b equals 1, n plus 1 equals 1, n equals 1 minus 1, which is 0. So my sum would now start from 0 instead of 1. So let me apply it here. This sum will be modified into 1 over 27 multiplying the double sum of a from 1 and then the other sum to infinity of b, sorry, not b this time, n from 0. Let me make this more evident. A from 1, a from 1, then n from 0. Okay, so this will now be a over 3 plus b plus 1. Alright, now I'm still going to bring back something we already now. Is that it is the Polygamma function. Yes, we already knew before that Polygamma m of z is equivalent to minus 1 to the power of m plus 1 times m factorial all over the sum to infinity of m from, sorry, infinity of n from 0 all into 1 over n plus z to the power of m plus 1. Okay, now something is happening here. Here, what are the equivalent terms? Z in this case is a over 3 plus 1. That is my z. Now this is 3 here, this is m plus 1. So if m plus 1 plus 1 is 3, then m has to be 2, right? M has to be 2. But something is not right here. We don't have 2 factorial, and we don't have minus 1 to the power of 3 is always a negative number, and there is no negative number here. So I'll just exchange this sum for it to now take this form by dividing both sides. I have minus 1 to the power of m plus 1 all over m factorial. Right, so wherever I see a sum that takes this form, now I'll just attribute it to Polygamma function like this. So now I'm having, in my case here, I have this sum here. Okay, let me just come under here and write it. I have 1 over 27 times the sum of the first, because I've not touched this one. Now this is the sum I'm working with, and my z is a over 3 plus 1 is a over 3 plus 1. So I now have the sum of here m plus 1 makes 3 for mine, so m has to be 2. I have 2, so I'm just making use of the Trigonometry function. Then my z is a over 3 plus 1. Okay, now divided by minus 1 to the power of 2 plus 1. 2 plus 1 is 3. So this will be minus 1, and what else? 2 factorial times, minus 1 times 2 factorial, which is 2 times 27 is 54. So I have minus 1 over 54 multiplying the sum to infinity of a starting from 1 all into my Trigonometry function. Now there's one other thing we're going to learn about Polygamma functions, and it is that, note, Polygamma m of z is equivalent to the integral of the negative minus the integral of t raised to the power of m minus 1 multiplying ln to the power of n to the power of m this is z, this is where z falls in. Then here I have then t all over 1 minus t dt. Okay, back to my sum. This sum will now be transformed into, okay, this is from 0 to 1. This sum will now be transformed into minus 1 over 54 all into the sum to infinity of a starting from 1 of, what else do I have? My z here is a over, this is a over 3. A over 3 plus 1. So this is the integral from 0 to 1 of t raised to the power of a over 3 plus 1, what else does it say? Minus 1 plus 1 minus 1, because you see minus 1. So plus 1 minus 1 is 0, so there's no use for writing it. Then my m is what? 2, since I'm working with Trigonometry function. So I have ln square t all over 1 minus t dt, and don't forget your minus sign from the integral here. So minus minus is plus. I now have 1 over 54, then extracting my integral sign. My integral sign from 0 to 1. Then what else here? Ln square 2, since ln square t, since these things has no relation with a, so they have there's no reason why they should be inside the sum. I only have inside the sum a starting from 1. I already have t raised to power a over 3, or rather, let me write t raised to power 1 over 3 to the power of a dt. Okay, so from here, remember what I said earlier, that when this sum starts from 1, it is gonna be 1 over, in my case, 1 over 1 minus t raised to power 1 over 3. Sorry, I said this in the first part of this tutorial. Minus 1, which is same as t raised to power 1 over 3 all over 1 minus t raised power 1 over 3. Okay, or rather, instead of writing this, I'll just leave it this way. So my integral will now take the form. I'll now have that this is 1 over 54 multiplying the integral from 0 to 1 of ln square t all over 1 minus t, then multiplying what the sum gave us, which is 1 over 1 minus t raised power 1 over 3 minus 1 dt. Okay, now I'm gonna share the integral for these two now. So I'm gonna have 1 over 54 all into the integral from 0 to 1 of ln square t all over 1 minus t multiplying 1 minus t raised to power 1 over 3. Then for the other one, okay, dt. Then for this other integral, minus 1 over 54 multiplying the integral from 0 to 1 of ln square t. Remember, I'm going to use everything here to multiply into the bracket. So I have ln square t over 1 minus t dt. Okay, so this is it. Now for the first part, before I continue, let me evaluate this place here. Note that, or rather, we already know that from sum of a GP that 1 plus x plus x squared is equivalent to 1 minus x to the power of 3 all over 1 minus x. So if I am to replace this x with t raised to power 1 over 3, I'll have that 1 plus t raised to power 1 over 3 plus t raised to power 2 over 3 is equivalent to 1 minus t raised to power 1 over 3 cube all over 1 minus t raised to power 1 over 3. Now, which is the same as 1 minus t all over 1 minus t cube root of t. So let me divide both sides by this. I'm dividing both sides by that. I'll have the 1 plus t plus t raised to power 1 over 3, plus t raised to power 2 over 3 all over 1 minus t is equivalent to 1 over 1 minus t raised to power 1 over 3. Okay, that is it. So from here, let me make substitutions. So now I have 1 over 54 multiplying the integral from 0 to 1 all into ln square t all over, what did I say this is now? This is going to multiply, this is going to be this. So I have all over 1 minus t and 1 minus t all into 1 plus t raised to power 1 over 2 plus t raised to the power 2, sorry, 2 over 3. This is 1 over 3, sorry. Two over 3 dt, which is the same as writing 1 minus t raised to the power of 2. Okay, now for this other one, I'll just introduce my sum notation. Sum to infinity of n starting from 0 all into the integral from infinity to 0 to 1, sorry, from 0 to 1 of t raised to the power of n multiplying ln square t dt. Okay, now remember what I did in the previous step as step 1 of this solution. I made it known to you that 1 over 1 minus t squared is equivalent to the sum to infinity of n starting from 1 all into n times t raised to the power n minus 1. So we've already known this, so I'm going to apply it now. I have that my integral is equal to, what do I have here? 1 over 54 multiplying the sum to infinity of n from 1 all into n first, then my integral of from 0 to 1 of t raised to the power of n minus 1 ln square t, then 1 plus t raised to the power 1 over 3 plus t raised to the power 2 over 3, okay, dt. Then the other part, this other one, I have minus 1 over 54 all into the sum to infinity of n from 0 of, remember what I said in the other part, the second derivative of the integral from 0 to 1 t to the power of n, sorry, dt. Now a similar thing I'm gonna apply here. In this place, if I'm expanding this with this, I'll be having t to the power of n minus 1 plus t to the power of n plus 1 over 3 minus 1 plus t to the power of n plus 2 over 3 minus 1. So if I'm to introduce the integral from 0 to 1, then my ln square t, sorry, let me write it on the other part, ln square t dt. I'll now apply Dirichlet's rule. I have d square over dn square all into the integral of what is here, t to the power of n minus 1 plus t to the power of n plus 1 over 3 minus 1 plus t to the power of 2 over 3 plus n minus 1 dt. Okay, now remember I said that the integral from 0 to 1 of t to the power of n plus k dt is the same as 1 over n plus k, alright, plus 1. Now if I modify k to become k minus 1, it will now be this minus 1, which is same as writing n plus k. Okay, so this is 1 over 54 all into the sum to infinity of n from 1 multiplying n, which have already been here, then the second derivative of, remember this rule, all of them has minus 1, so k I've defined itself. I have 1 over, what is k here? K in this place is 0, so I have 1 over n. Then for this other one, I'll have plus 1 over n plus 1 over 3, then plus 1 over n plus 2 over 3. That is for this sum. And then for this other sum, I have minus for the other sum I have minus 1 over 54 multiplying the sum to infinity of n from 0 all into the second derivative of, now evaluating this integral here, I have 1 over n plus 1. Okay, so now remember what I said, the second derivative of 1 over n plus b is equal to minus 1 square 2 factorial all over n plus b to the power of 2 plus 1, which is 3. So anyway I see this or anything related to it, I'll quickly change it. So in this case, back to my sum, I'll have that this is minus 1 square 2 factorial all over 54 multiplying the sum and from 0, from 1 of n multiplying, this is 1 over, first one is only n, so I have 1 over n cubed plus 1 over n plus 1 over 3 cubed plus 1 over n plus 2 over, is it 2 over 3? Yes, 2 over 3 cubed. Okay, then for this one I have minus 1 square 2 factorial all over 54 all into the sum to infinity of n from 0 all into 1 over n plus 1 cube. Okay, so now I'll just separate the sum for the first, then leave the sum for the two remaining one. Okay, I'll just bring out the sum for all of them. I have, this is minus 1 square 2 factorial all over 54 for the first sum, and starts from 1 of, this is 1 over n square because this n will take care of the first n. Now for this other part I'll just give them one sum, since I'm going to use them together using one principle. So I have this multiplying the sum to infinity of n starting from 1 all into n over n plus 1 over 3 cube plus n over n plus 2 over 3 cube. Okay, now for this last one, remember what this looks like, zeta function, right? So this is minus 2 over 54 is the same as 1 over 27 multiplying what? Zeta 3. Okay, now let's go over to this side. This is, permit me to write 1 over 27 zeta 2, this is my zeta 2, because this is still the other way of writing zeta function. Then from here, remember what I said before, Trigonometry function for any number is defined as minus 1 to the power of okay, this is not the main format of Trigonometry function. I'm missing something. Let me see, write this. Okay, before I continue, let me bring in this one to this other side. So this is minus 1 over 27 zeta 3, then here plus minus 1 square 2 factorial all over 54, sorry, 54 multiplying the sum to infinity of n starting from 1 all into. Now if I'm to decompose this into partial fraction, I'll have, yeah, this is minus 1 over 3 multiplying n plus. Okay, I need to do something else before this. Now this sum originally was this here, this expression was n over n plus 1 over 3 cube. Then the other one was n all over n plus 2 over 3 cube. So now if I change this sum for it to start from 0, this will now become n plus 1, and instead of being ordinary n, this one will also be n plus 1. And then this one too will change to n plus 1. So at the end I'll have here to be n plus 2 over 3. Then here will be n plus 5 over 3. Okay, now decomposing it into partial fraction. Sorry, I missed to include here. Decomposing them now into partial fraction, I have this one now becomes 1 over 27 zeta 2 minus 1 over 27 zeta 3 plus, remember I want to factorize those after decomposing these into partial fraction. Now into partial fraction, I want to first work with those that have cube, then the other one for those that came with squares. So I have, you notice that those that have cube has a minus sign on them, so this is plus minus 1 to the power of what is here already, 2. Then this is 2 plus 1 times 2 factorial, all dividing 54 all into its sum of n from 0, and for the other one I have 1 over 3 multiplying n plus 4 over 3, 4 over 3 cube plus 2 divided by n plus 5 over 3 cube. Now let me give another sum for these ones that are square. Okay, so it will now be plus minus 1 square 2 factorial all over 54 multiplying the sum to infinity of n starting from 0, starting from 0 of, what are they? The first one, this 1 over n plus 4 over 3 cube, then the other one plus 5 over 3 to the power of, sorry, this is square, not cube. Now remember what Polygamma function states, that Polygamma m of z for any variable z is same as minus 1 to the power of m plus 1m factorial all into the sum to infinity of n starting from 0 of 1 over n plus z to the power of m plus 1. Okay, this is it. Now if you let me write this first, that this is 1 over 27 minus, sorry, zeta 2 minus 1 over 27 zeta 3 multiplying, in this case, plus if you watch these two here, this is 2 factorial like m factorial, then 2 plus 1 like m plus 1 here, then 3 is 2 plus 1, so I'll have 1 over 54. Okay, so while decomposing this into partial fraction, I missed something here. There's a 3 here, so if there's a 3 there, this one will also have its own 3. So that 3 will multiply these 3 here, will be factorized to multiply 54, so that I'll have 54 times 3, which are 162. Then all into the two sums, sum to infinity of n starting from 0 of 1, sorry, I shouldn't have written this sum again. I'll just open my bracket, and what do I have? These two now have obeyed the rules of Polygamma function, so this is now, since m plus 1 is the same, m plus 1 is the same as 3, that means m is 2, so this is now digamma. Digamma what first? Let me clean this. Digamma 4 over 3 here. 4 over 3 plus 2 digamma 5 over 3. Okay, now in this other part I have 2 over 57. 2 divided 57, I'm left with plus 1 over 27 all into this other sum alone on its own part here is obeying the rule of digamma function. It is minus 1 to the power of 1 plus 1 all into 1 factorial. 1 factorial is 1, then the rest is the sum of n from 0 all over 1 over a z here. 1 plus 1 all into multiplying 1 factorial, then also multiplying the sum to infinity of n starting from 0 of 1 over n plus z to the power of 1 plus 1. If you notice, this is 2, this is 2, so the two sums obey the rule of digamma function. Digamma is when m is 1, so this is digamma. What is here? 4 over 3. Digamma 4 over 3 and 5 over 3 plus digamma 5 over 3 Okay, so note that trigonometry 4 over 3 is equivalent to minus 26 zeta 3 plus 54 minus 4 pi cube all over 3 root 3. Then trigonometry 5 over 3 is equivalent to minus 26 zeta 3 plus 27 over 4 plus 4 pi cube all over 3 root 3. So now I'll just simply substitute these values for these. So first let me write out these ones. I have that my double sum is equivalent to 1 over 27 is equivalent to 1 over 27 zeta 2 minus 1 over 27 zeta 3 plus 1 over 162 all into 1 over 162 all into, now here let me bring it in the value of trigonometry 4 over 2 first, which are minus 26 zeta 3 plus 54 minus 4 pi cube all over 3 root 3. Now that is 4 over 3. Then plus 2 multiplying trigonometry 5 over 3, which in this case it will be plus trigonometry 5 over 3. Now when 2 multiplies minus 26 zeta 3, I'll have minus 52 zeta 3. Then when 2 multiplies 27 over 4, I have plus 27 over 2. Then when 2 multiplies this last one, I'll have 8 pi cube all over 3 root 3. Okay, let me close my brackets. Now for this other one, for these other parts, Let me quickly erase this. Please note that Trigonometry, sorry, this time around, please note that diagamma 4/3 plus diagamma 5/3 is equivalent to 4 pi square all over 3 minus 45 over 4. Okay, so applying it here now, I have remember this, let me write it under. I have this plus 1/27 all into then the value of the sum of the both, which is this. I have 4 pi square over 3 minus 45 over 4. Okay, so from here I have, now before I start working, we already know that, okay, in case you don't know, zeta 2 is the same as pi square over 6. So if I'm to rearrange this in terms of zeta 2, I'll have, this is pi over 3, right? So if I want to make here 3, this is something as 3 times 2. So here, let me multiply here by 2 and here by 2, so that this 2 can cancel out. This will be pi square over 3 as we had here, then still multiplied by 4, then here by 4. So whatever I have here is equivalent to 8 zeta 2. So the next is expanding the bracket. I'll have 8/27 zeta 2. Let me bring in the first. The first is 1/27 zeta 2, then plus 8/27 zeta 2, then minus 1/27 zeta 3. So this is 1/27 zeta 3, and then if we evaluate, minus 26 minus 52 all over 162 minus 26 minus 52 all over 162, we'll be getting minus 13 all over 27. So let me apply it here. This minus 13 over 27 zeta 3 then what else is remaining? Then we'll work with the constants. Okay, leaving something behind. Then here, this is 8 pi cube over 3 root 3. This is minus 4 pi cube over 3 root 3. So when the two of them add, I'll have 8 minus I have that 8 minus 4 is same thing as 4, so the addition of the both will give me 4 pi cube over 2 over 3 root 3. Now when I multiply it by 1 over 162, I'll be left with 4 can divide 162, giving me 2 here, 2 remains, and 2 here. 1. Okay, 4 cannot actually go through. If I reduce it, I'll be left with 4 pi cube all over 3 times 81 root 3. Now, if I am to rationalize this surge, I'll be left with that this is 2 root 3 all over 7 to pi cube. Okay, now let me just enter it here. Plus 2 root 3 all over 7 to 9 pi cube. Okay, let me erase these parts. Okay, now the remaining now is the constant stems. The sum of this when divided by this 54 plus 27 over 2 when divided by 162 minus 1 over 27 multiplying 45 over 4. This gives me 0. So other constant stems cancels out here. Now before I continue, I gave you a promise. Remember, I told you to guess a number, then I'll give you 2 assertions that will always work for those 2 numbers. Okay, now for the first number, now the first assertion, is that you never choose a complex number. I mean, there are different types of numbers. There are real numbers, rational numbers. You never thought of a complex number. And then the second is that if assuming that this number is not 0, then it is something either greater than 0 or less than 0. If I am wrong, go and prove me wrong in the comment section. Alright, now the last phase of this solution is this 1 over 27. I'm working with this now. 1 over 27 plus 8 over 27 is the same as 1 over 3. So I'm permitted to write 1 over 3 theta 2 here. Then what else? Now minus 1 over 27 minus 13 over 27 is equivalent to minus 14 over 27. So I'm still permitted to write this. Now, minus 14 over 27 zeta 3 then the last one plus 2 root 3 all over 7 to 9 pi cube. Okay, I've come to the end of this tutorial. Now compare the first solution and then the second. Tell me the one you like best. Don't forget to show me love by liking this tutorial video. Then if you're watching me from YouTube, don't forget to subscribe to this channel. If you're watching me from other sites, don't forget to share this so that it can reach to everyone and the knowledge can be spread. Thank you for watching.